Hey guys, this is Mr. Galoya. I'm back here with you again. We're going to spend a little bit of time talking about how things move down hills, and it's really nothing kind of new for you. I think, you've been in a car as it goes down a hill, or maybe you've been sledding or skiing. This is kind of motion down hills. Well, so what exactly, where have we exactly been in this class? Well, we've talked about constant velocity motion, and this is basically, like a cruise control. It's an object that's staying at one speed, and, we had like an equation for that. And then we've talked about objects that get faster, and then objects that kind of get slower. Both of these really are accelerative motions. In one case we have then a positive acceleration, and then in the other case we have a negative acceleration. And we basically see parabolas on the position time graph, and we see diagonals then on the velocity time graph. Well, in what we've been really discussing and the projects we've been building, we've put motors and gears or pulleys or fans on the motor, and we've allowed then the batteries typically then to power the object. But we really can see the same sort of thing with the influence of gravity, right? And gravity can be the agent that then creates the motion. And this basically is the motion that we see with cars or balls or objects on hills. And when we talk about hills, there's kind of several other words that you'll find in physics books. We can talk about then ramps, or another sort of phrase that's often used is the inclined plane. Now, this type of motion is seen a lot in sports and in cars. If you're into skiing or sledding, maybe you've gone, sledding down KU, some of the hills there. I know I used to take my kids then down, the hill by the stadium, the Campanile Hill, and you guys have probably been in cars that have gone down hills. Well, I'm going to show you a movie now of my Honda kind of going down a hill, and I'm going to kind of pause my notes and kind of write down maybe some of your observations. So I'm going to kind of pause now and show you this movie. So what were some of your observations? What did you see my speedometer do? Well, as you go down the hill and you're coasting down the hill, the speedometer the speedometer then increases, right? And that's exactly, that's exactly what we're saying, happened with this accelerative motion here, right? That's what we would see our speedometer do when we put the pedal to the metal. We would see the speedometer kind of go up. Or if we got our foot on the brake, it would go down. Well, so for objects coasting down a hill, we really see the same sort of an effect. It's an acceleration, but instead of a motor kind of causing all this, we have the effects of gravity that is causing this acceleration. Now let's kind of flip over to the flip side, and I'm just going to put my other sheet up. For you guys, it's kind of the flip side. Well, this was a very, very important discovery, and Galileo kind of makes this discovery, around the 1600s. He publishes a book, The Two New Sciences, and this book explains a little bit about how objects then move down these inclined planes, or we would call them hills or ramps. And Galileo kind of discovers this whole idea of how things move on inclined planes, and it was just really incredible because at this point clocks, reliable timepieces and clocks and stopwatches had not yet been invented. And Galileo would create these very long ramps, and he would use things like pendulums, the swinging of a pendulum, or he would use this device called a water clock. Occasionally he might have used this pulse to try to then figure out how does an object move down this inclined plane. Now there's a couple more short movie clips I'm going to show you, and I'll kind of pause the video for that and I'll show you those.
The Catholic Church declared much of Galileo's work heretical. They banned his books and forced him to stand trial for his writings about a sun-centered universe. Late in his life, under house arrest, he began to examine his own early work on the physics of motion.
You get this extraordinary situation that he'd made these really great discoveries in the study of motion right back in about 1604, something like that, and he'd written it up in a Latin text back then. But it's so many other exciting things happened to Galileo, he never seems to have got around to publishing it. So it was in a way a blessing that he was put in house arrest. He finally made him get round to writing these results up.
Galileo had spent years trying to find physical proof that the Earth moves. Now he set out to understand the mathematics of motion. He wondered how the speed of an object might vary while falling, but the motion of a falling object was difficult to measure.
It all happens just a bit too fast for you to see what is going on. Galileo hit on this wonderful idea of slowing down the motion. So instead of trying to watch a thing falling, he rolled balls down very gentle slopes so that the speed built up very, very slowly.
Galileo hypothesized that the rolling balls would accelerate uniformly like they did in free fall, which he established experimentally earlier. To test his theory, he rolled balls down an inclined plane to slow them down enough to be able to analyze the motion. Based on Galileo's experimental notes from his book Two New Sciences, Professor Roberto Caffarelli built a replica of Galileo's original inclined plane and used it to recreate his experiments, hoping to discover how Galileo was able to measure acceleration.
Galileo studied the inclined plane, slowing the motion of falling bodies until he was able to observe the phenomena. He was able to measure exactly how fast a ball would roll, timed with the swing of a pendulum. Galileo was sure that the steady acceleration must be governed by a mathematical rule.
So he takes this very gentle inclined plane and he lets the ball roll down. and he watches how that ball speeds up, and he measures how far it goes in a certain time. And then he makes his first empirical discovery that if in the first unit of time it goes 1 unit of distance, in the next unit of time it travels 3 units of distance, and in the next 5, and then the next 7. So it has this beautiful numerical progression, 1, 3, 5, 7.
Galileo found that the velocity acquired equaled the acceleration multiplied by the time elapsed, and that the distance traveled was always proportional to the square of the time elapsed.
And he really is entranced by this. He knows he's made a huge discovery.
He had found mathematical rules for accurately predicting the motion of objects on the inclined plane, universal laws that apply to all falling bodies.
Underneath this beautiful empirical law that he found a deeper law, clearly a deeper law, using mathematical logic and deductions. And this was actually the key to all the later great successes, first of Newton and then of Einstein and all the other wonders of modern science.
This experimental apparatus provided a demonstration of the Galilean law of the natural fall of bodies, which stated that the spaces traversed from a position of rest are proportional to the squares of the times of fall. The pendulum attached to the inclined plane was swung at the same time as the small ball was released. In each successive oscillation of a pendulum, the sphere traversed spaces that increased, in accordance with a sequence of odd numbers. In the first oscillation period, the sphere traversed a given interval from its rest position. In the second period, it travelled 3 spaces. In the third period, 5 spaces. In the fourth period, 7 spaces, and so on. It follows that the sphere traverses 4 spaces in 2 periods from the rest position, 9 spaces in 3 periods, 16 spaces in 4 periods, and so on.
Okay, I'm back here, and so Galileo kind of does all this, and he kind of makes all these discoveries about how objects move along the inclined plane. Well, we're going to be able to kind of experiment with this too, and we'll be able to take a movie of a little Pasco car going down an inclined plane, and you're going to kind of make your own movie. I'm going to show you mine, but you'll kind of make your own movie, and then we can use video analysis to actually come up with the acceleration and the speeds of the objects as they move down the inclined plane. You know, one thing we'll study later is, and you guys probably kind of know this already, but the angle of your hill or your inclined plane changes really the motion or the acceleration. And again, we can call this angle theta. And we'll kind of get into this a little bit later in the class, how theta can actually change your acceleration and some of the forces that we see on the inclined plane or on the hill. Well, really, there's no new sort of equations. There's really no new sorts of equations here. We're just talking about an acceleration. And again, the key thing is that we don't really need any motors. You know, to do all this, we can just use the effects of gravity itself. So no new equations. We still have the how fast equation, Vf equals Vi plus At. And we have the how far equation. Again, some books write that delta x equals Vit plus 1/2 At squared. Okay, that's how some books write the equation. Other books might write the equation x sub f equals x sub I plus Vit plus 1/2 At squared. And that again corresponds to an equation for a parabola or your parabolic equation. That would be c plus bt plus At squared. Okay, that's what you might see in a math course for a quadratic equation. Well, these problems that you might see aren't really that challenging. You know, let's say Galileo releases a ball from rest. Again, from rest kind of means what? Well, it means that your initial velocity is 0. So he's releasing this ball from rest along an inclined plane that's providing an acceleration of 0.4 meters per second. So that's really then what our acceleration here is in this problem. There's our A. If it takes 5 seconds, so that's going to be our T, for the ball to reach the bottom of the ramp, what is its velocity at the bottom of the ramp, and how long is the ramp? So we've got this ramp here. Galileo releases this ball, and this ball is going to reach some sort of, it's going to accelerate, so its velocity is going to be getting greater as it goes down the ramp. It reaches some sort of velocity, and we can determine what that velocity is, and we can kind of determine how long the ramp is. So if we use our how fast equation, let me make sure that's going to get on there. If we use our how fast equation, we would have 0 plus our acceleration, 0.4 meters per second, times 5 seconds. One of my seconds then cancels, and I have 0.4 times 5. That's going to be then 2 meters per second. That would be how fast. If we want to then get how long the ramp is, that would be like a delta x, right? That would be like a displacement idea. So we could say delta x equals VIT plus 1/2 AT squared. Okay, so we could say, well, this whole term goes to 0 because your VI is 0, plus 1/2 times A, but that's our 0.4 meters per second, times T squared. Well, that's going to be 5 seconds, and then we have to square everything. So we're going to take a half of 0.4 times in 25. So again, I'm going to just use a calculator. So 0.5 times 0.4 times 25, and we get then that the ramp is 5 meters long. Okay, so again, not super challenging. We've got, again, 2 equations. We got the how far and how fast equations. Okay, we'll talk to you later, kids. Bye.